Welcome, everyone. This is part 7 in our series on supervised sentiment analysis. The focus of this screencast is on feature representation of data. There are really two things I'd like to do. First, just explore some ideas for effective feature representation in the context of sentiment analysis. And second, cover some of the core technical concepts that surround feature representation that you do well to have in mind as you write new feature functions and optimize models. Let's begin in a familiar place, which is n-gram feature functions. To this point in the series of screencasts, I've been just focusing on unigram feature functions. That's also called the bag of words model. And we can easily generalize that idea to bigrams and trigrams and so forth. All of these schemes will be heavily dependent on the tokenizer that you've chosen because, of course, in the end, for every example we represent, we are simply tokenizing that example and then counting the tokens in that example. This can be combined, of course, with pre-processing steps. In part 2 in this series, I covered the pre-processing idea of neg marking, which is essentially to mark words as they appear in a heuristic way in the scope of negative morphemes as a way of indicating that, for example, good is positive in normal context, but might become negative when it is in the scope of a negation like not or never. We would handle that as a pre-processing step, and that would just create more unigrams that our tokenizer would turn into tokens and then would be counted by these feature representation schemes. A hallmark of these feature approaches is that they create very large, very sparse feature representations. You are going to have a column in your feature representation for every single word that appears anywhere in your training data. And another important thing to keep in mind about this approach is that by and large, they will fail to directly model relationships between features. Unless you make some special effort to effectively interact these features, all you'll be doing is studying their distribution with respect to the class labels that you have. And it's very unlikely that you'll recover in any deep way the kind of underlying synonymy of words like couch and sofa, for example. And this is a shortcoming that we might want to address as we move into distributed representations of examples and deep learning. So for a first technical concept, I would like to just distinguish between feature functions and features. And to do this, I've just got a fully worked out example here using tools from scikit-learn that I think will make the importance of this distinction really clear and concrete. So in cell 1, I've just loaded a bunch of libraries. In cell 2, I've got my standard kind of lazy unigrams feature function, which is taking in a string text, downcasing it, and then simply splitting on white space. And then the counter here is just turning that into a count dictionary, mapping each token to the number of times it appears in this example, according to our tokenizer. That'll be fine for now. In cell 3, I have a tiny little corpus that has just 2 words, A and B. In cell 4, I create a list of dictionaries by calling unigrams phi on each of the texts in my corpus here. So that gives me a list of count dictionaries. In 5, I use a dict vectorizer as covered in a previous screencast. And what that's going to do is when I call fit transform on my list of feature dictionaries, it will turn it into a matrix, which is the input that all of these scikit machine learning models expect for their training data. And in cell 7, I've just given you what I hope is a pretty intuitive view of that design matrix. Underlyingly, it's just a NumPy array. But if we use pandas, we can see that the columns here correspond to the names of each one of the features. Because we have just 2 word types in our corpus, there are 2 columns, A and B. And each of the rows corresponds to an example from our corpus. And so you can see that our first example has been reduced to a representation that has 3 in its first dimension and 0 in its second, corresponding to the fact that it has 3 A's and no B's. Example 2, AAB, is represented as a 2 in the first column and a 1 in the second column, and so forth. So that's a first distinction. We have this feature function here, which is like a factory. And depending on the data that come in for our corpus, we're going to get very different features, which correspond to each one of the columns in this feature representation matrix. Let's continue this a little bit and think about how this actually interacts with the optimization process. So in cell 7 here, I've just repeated that previous matrix for reference. In cell 8, I have the class labels for our 4 examples, and you can see there are 3 distinct classes, C1, C2, and C3. I set up a logistic regression model, although that's not especially important. It's just a useful illustration. And I call fit on my pair XY, that is my feature representations and my labels. And that's the optimization process. As part of that, and for a convention for scikit, the optimization process creates this new attribute coef underscore and this new attribute classes underscore. These coef here, these are the weights that we learned as part of the optimization process. And of course, classes corresponds to the classes it inferred from the label y that we input. And here I'm just using a pandas data frame again to try to make this intuitive. It's really just a NumPy array, this coef object here. But you can see that the resulting matrix has a row for each one of our classes and a column for each one of our features. And that's a useful reminder that what the optimization process for models like this is actually doing is learning a weight that associates class feature name pairs with a weight, right? So it's not just that we learn individual weights for features, but rather we learn them with respect to each one of the classes. And that's a hallmark of optimization for multi-class models like this one. And then in cell 12, I've just shown you that you can actually use the coef and this other bias term intercept underscore to recreate the predictions of the model. All you're doing is multiplying examples by those coefficients and adding in the bias term. And this matrix here is identical to what you get in scikit if you simply directly call predict proba for predict probabilities on your examples. Let's turn back to what we're trying to do to create good models, having those ideas in mind. So let's just cover a few other ideas for hand-built feature functions that I think could be effective for sentiment. So of course, we could have lexicon-derived features. I earlier showed you a bunch of different lexicons, and that could be used to group our unigrams. So we could have these feature functions work in conjunction with a bag of words or bag of n-grams model, or we could use them to replace that model and develop a sparser feature representation space. We could also do the negation marking that I mentioned before, and we could generalize that idea. So many things in language take scope in a way that will affect the semantics of words that are in their scope. So another classical example besides negation is these modal adverbs like quite possibly or totally. We might have the idea that they are modulating the extent to which the speaker is committed to masterpiece or amazing in this case, and keeping track of that semantic association with simple underscore marking of some kind might be useful for giving our model a chance to see that these unigrams are different depending on their environment. We could also have length-based features, and that's just a useful reminder that these don't all have to be count features. We could have real valued features of various kinds, and they could signal something important about the class label. Like, for example, I think neutral reviews, 3-star reviews, tend to be longer than 1- and 5-star reviews. So might as well throw that in. And we can expand that idea of float valued features a little bit more. I like the idea of thwarted expectations, which you might keep track of as the ratio of positive to negative words in a sentence. The idea being that very often if that ratio is exaggerated, it's telling you the opposite story that you might expect about the overall sentiment. Many, many positive words stacked up together might actually be preparing you for a negative assessment and the reverse. But the important thing about this feature is that it wouldn't decide for you what these ratios mean. You would just hope that it was a useful signal that your model might pick up on as part of optimization to figure out how to make use of the information. And then finally, we could do things, various kinds of ad hoc feature functions to try to capture the fact that many uses of language are non-literal and might be signaling exactly the opposite of what they seem to do on their surface. Like, not exactly a masterpiece is probably a pretty negative review. It was like 50 hours long is not saying that it was actually 50 hours long, but rather with hyperbole indicating that it was much too long or something like that. And the best movie in the history of the universe could be a ringing endorsement, but it could just as easily be a bit of sarcasm. Capturing those kind of subtle distinctions is of course much more difficult, but the hand-built feature functions that you write, well, you could try to capture it, and if they have a positive effect, then maybe you've made some real progress. And that's a good transition point to this topic of assessing individual feature functions. As you can see, the philosophy in this mode of work is that you write lots of feature functions and kind of see how well they can do at improving your model overall. You might end up with a very large model with many correlated features, and that might lead you to want to do some feature selection to weed out the ones that are not contributing in a positive way. Now, scikit-learn has a whole library for doing this called feature selection, and it offers lots of functions that will let you assess how much information your feature functions contain with respect to the labels for your classification problem. So this is very powerful, and I encourage you to use them, but you should be a little bit cautious. Take care when assessing feature functions individually, because correlations between those features will make the assessments very hard to interpret. The problem here is that your model is holistically thinking about how all these features relate to your class label and figuring out how to optimize weights on that basis. Whereas the feature function methods, many of them just look at individual features and how they relate to the class label. So you're losing all that correlational context. And to make that a little concrete, I just cooked up an example here, an idealized one that shows how you could be misled. So I have three features, X1, X2, and X3, and a simple binary classification problem. And I use the chi-square test from feature selection to kind of assess how important each one of these features is with respect to this classification problem. And what I found is that intuitively, it looks like X1 and X2 are really powerful features. And that might lead me to think, well, I'll drop the third feature and include just 1 and 2 in my model. So far, so good. However, if we thoroughly explore this space, what we find is that in truth, a simple linear model performs best with just feature X1, and actually including X2 hurts the model, despite the fact that it has this positive feature importance value. So what we really ought to be doing is using just this single feature, but these methods can't tell us that. And even a positive feature selection value might actually be something that's at odds with what we're trying to do with our model, as this example shows. So ideally, what you would do is consider more holistic assessment methods, which Scikit also offers. This would be things like systematically removing or perturbing feature values in the context of the full model that you're optimizing and comparing performance across those models. This is much more expensive because you're optimizing many, many models. So it might be prohibitive for some classes of models that you're exploring, but if you can do it, this will be more reliable. However, if this is impossible, it might still be productive to do some feature selection using simpler methods. You should just be aware that you might be doing something that's not optimal for the actual optimization problem that you've posed. Okay, and the final section of this screencast is a kind of transition into the world of deep learning. I've called this distributed representations as features. This is a very different mode for thinking about representing examples. What we do in this case is take our token stream as before, but instead of writing a lot of hand-built feature functions, we simply look up each one of those tokens in some embedding that we have. For example, it could be an embedding that you created in the first unit of this course, or it could be a glove embedding or a static embedding that you derived from BERT representations, and so forth and so on. The important thing is that each token is now represented by a vector. And that could be a powerful idea because in representing each of these words as vectors, we are now capturing the relationships between those tokens. We might now have a hope of seeing that sofa and couch are actually similar features in general and not just with respect to the class labels that we have. So that's the idea why this might be powerful. So we take all those vectors and look them up. However, for all these classifier models, we need a fixed dimensional representation to feed into the actual classifier unit. So we're going to have to combine those vectors in some way. And the simplest thing you could do is combine them via some function like sum or mean, right? So I would take all of these things, for example, and take their average, and that would give me another fixed dimensional representation, no matter how many tokens are in each one of the examples. And that average vector would be the input to the classifier. So if each one of these vectors has dimension 300, then so too does the feature representation of my entire example. And now I now have a classifier which is processing feature representations that have 300 columns. Each dimension in the underlying embedding space now corresponds to a feature. And that's the basis for optimization. And I'd say an eye-opening thing about this class of models is, despite them being very compact, 300 dimensions versus 20,000 that you might have from a bag of words model, they turn out to be very powerful. And this final slide here just shows you how to implement those using tools and other utilities for our course. So I'm going to use glove, and I'm going to use the 300-dimensional glove space, which is included in your data distribution. In 4 and 5 here, we just write simple feature functions, and the hallmark of these is that they are simply looking up words in the embedding and then combining them via whatever function the user specifies. So the output of this is directly a vector representation of each example. In cell 6, we set up a logistic regression as before. Of course, it could be a much fancier model, but logistic regression will do. And then we use SST experiment almost exactly as before. The one change we need to remember to make in operating in this mode is to set the flag vectorize equals false. We already have each example represented as a vector, so we do not need to pass it through that whole process of using a dict vectorizer to turn count dictionaries into vectors. And as I said before, these turn out to be quite good models despite their compactness. And the final thing I'll say is that this model is a nice transition into the recurrent neural networks that we'll study in the final screencast for this unit, which essentially generalize this idea by learning an interesting combination function for all the vectors for each of the individual tokens.